Imagine flying over a perfectly calm ocean. The weather is clear, visibility is high. But when you look down at your instrument panel, the needle on your compass starts twitching before spinning wildly out of control. This exact scenario happened in December 1945. 5 experienced U.S. Navy pilots departed Florida for a routine training mission over the Atlantic, known as Flight 19. An hour and 45 minutes after takeoff, the mission commander radioed the flight tower. He sounded disoriented, stating that he couldn't see land and that everything looked strange, even the water. After a few fragmented, panic-stricken messages, the transmission cut out. The tower heard nothing but silence. The source of these vanishings is found in the physical environment, a series of natural traps extending from the ocean floor to the atmosphere. To understand how this works, we have to start at the deepest layer. Millions of years ago, an underwater volcano formed the island of Bermuda. When that volcano cooled, it left behind massive deposits of basalt rock across the seafloor. This map illustrates how this basalt creates an immediate hazard. The rock contains extremely high concentrations of magnetite. Normally, a compass points to the magnetic North Pole, which sits roughly 1,200 miles away from the geographic true North Pole. In this region, the sheer volume of magnetite creates a localized pole that shifts a compass needle up to 10 degrees. Investigators believe this magnetic interference disoriented Lieutenant Charles Taylor. On his final flight, he became convinced he was over the Florida Keys and turned his squadron northeast to find the mainland, unaware he was actually over the Bahamas and flying deeper into the open ocean. The squadron flew aimlessly until their fuel tanks ran dry, eventually crashing into the Atlantic. Even the military rescue planes sent to find them met a similar fate. Witnesses reported seeing an explosion far out on the horizon, likely caused by a known fuel leak vulnerability in the search aircraft. The basalt layer systematically strips a pilot of their ability to trust their foundational navigation tools, setting the stage for total disorientation. Moving up from the basalt rock, the deep seafloor presents a second hazard. Massive pockets of methane gas are trapped just under the sediment in the form of methane hydrates. When underwater tectonic plates shift or submarine landslides occur, these hydrate pockets destabilize. This forcefully ejects immense plumes of methane gas up toward the surface. This diagram demonstrates what happens when a ship is positioned directly above a blowout. The sudden influx of gas bubbles drastically reduces the water's density. The aerated, foamy water loses its ability to support weight, causing a floating vessel to instantly lose buoyancy and sink. This geological hazard can reach the sky, too. In January 1948, the Star Tiger passenger plane disappeared over the Atlantic without making a distress call. Because the pilot was intentionally flying at only 2,000 feet to avoid high winds, researchers theorized the plane was uniquely vulnerable to these gas plumes. At that altitude, a massive release of highly flammable methane could potentially reach the engines and ignite them without warning. The deep sea harbors volatile chemical traps capable of reaching up and erasing both ships and aircraft. The final layer of the trap operates above the water. When dry, hot air blowing off the Sahara Desert meets the warm, humid moisture of the Atlantic Ocean, the atmospheric instability spawns intense hurricanes. By the time these storm systems travel thousands of miles along the global wind currents and enter the Bermuda region, they have absorbed enough thermal energy to become incredibly violent. Navigating massive weather fronts requires precision, which is a problem when equipment fails. In December 1948, a DC-3 passenger plane flew into this exact corridor. The flight departed Puerto Rico with severely low batteries and a malfunctioning radio transmitter. Operating over a pitch-black ocean in the middle of the night, the crew lost their two-way communication and could no longer relay their coordinates to the mainland. When magnetic rocks disable your compass and faulty batteries silence your radio, the region's aggressive storm corridors ensure that any minor navigational error becomes fatal. The Bermuda Triangle is a rare geographical overlap where deep-sea magnetism, methane deposits, and hurricane corridors stack directly on top of each other. As global temperatures rise and warm the oceans, the physical boundaries of this high-risk zone could expand or shift entirely, pushing these hazards into new flight paths. Which leaves an important question. If you were piloting a plane over a completely dark ocean and your instruments suddenly contradicted what you saw out the window, would you trust your compass or your own eyes? Let me know what you would do in the comments below. And if you want to explore what would happen to our oceans if Antarctica melted, click the video right here on screen.